Okay, so what about this first one? They're asking us, it says use figure 510 to determine the velocity of the airplane that is speeding up. Now that one's actually given to you. You can just look right on the solutions here. It's the one kind of in the left middle of that first page, page 26. So they want us to know the airplane that's speeding up. Is that airplane A or B? A. Okay, everybody agree because the velocity is increasing with time. At 1 second, what's the velocity of airplane A? 74. We're just reading the graph, aren't we? Because in a velocity time graph, remember what that does for us. For any time that we choose, time is on the horizontal axis. It's giving us on the vertical axis, so the vertical coordinate of any point, the y-coordinate, gives us the velocity. So the point would have coordinates 174, wouldn't it? What about at 2 seconds? I'll read it again. 78, good. At 2.5 seconds? 80. Okay, meters per second. Good. Number 14, use the factored label method to convert the speed of the airplane whose motion is graphed in figure 5.6. So that's 75 meters per second. We need to convert to kilometers per hour. Well, I don't like the way they do this. We can do this better. So let's look at how we've talked about this. So we're starting with 75 meters per second. And we want to convert that into kilometers per hour. So what's our process here? Somebody explain for us how we do this. What are we going to multiply by? Sheldon, you look like you have an idea there.
So don't you just start off with the meters first?
Okay, yeah, we could. Sure. Ultimately we're gonna have to turn the meters into kilometers and the seconds into hours. Good. So we're gonna multiply by a factor, right? What's the value of that factor gonna be always?
It's something over 1. Like
Okay, so the numbers are gonna be something. You're right, but the overall value of the factor, I'm multiplying by something that's not gonna change the value. It's just gonna change the units, right? So it equals 1. In the sense that the quantity on the top and the quantity on the bottom have to be the same amounts, right? Just different units. Okay, so let's focus, before we put any numbers in, you're exactly right, let's focus on the units. What's gonna go on the bottom? Meters, and we know that before we do anything else because the whole goal is we wanna cancel the meters, right? So what goes on top? Kilometers. And now we just have to say a certain quantity of kilometers and an equivalent quantity of meters. What's the convenient one? 1 kilometer, 1,000 meters. Good, and look where we are. We're halfway done. We've now got the unit on top that we want, which is kilometers. Done with the distance part. Now we need to do the time part. We're going to multiply by another changer. So we have to go from seconds to hours. Do we know how many seconds are in an hour? Okay, 3,600. If you know that, you can do it in one fell swoop. If you don't remember that, what else could you do? Yeah, go to minutes and then from minutes to seconds. Let's do that. So let's see, we want to go from seconds. So what has to go on top? Seconds. You need to be able to cancel it. Good. And then on the bottom? Well, ultimately hours, but we're gonna have a pit stop at minutes. So that's good. We got rid of the seconds and replaced them with minutes. We have to come up with equal quantities of minutes and seconds. So probably 1 minute is 60 seconds. And then now we have to go all the way from minutes to hours. Good. So we're going to cancel the minutes, leave us with hours. 1 hour is 60 minutes. I could just as easily have said 10 hours or 600 minutes, but that would just be a dumb thing to do. But it would work, wouldn't it? Right? This wouldn't make any sense. And our units are perfect. Kilometers per hour. So now we just have to figure out what's the numerical part. Well, we just put it in our calculator and see. If I multiply straight across, I'm just going to get 75 times 60 times 60 divided by 1,000, right? 1,000 times 1 times 1. So 3,600, 75 times, so, I don't know what's that gonna be, 30, that's gonna be. So what's it, what are we gonna get, like a 270, yeah, so it'd be really be like 266.6 probably, I'm guessing, right? It just rounds to 270, is that right? Or is it actually 270? Oh, did you? Okay, yeah, okay. Well, either way, how many sig figs are there? 2, so we can only keep 2, so there's our, right, it works, okay? We don't have to round it at all. 270 kilometers per hour. Make sense? Okay, questions? No biggie? Okay, good. And this group is doing so well. This small class makes all the difference, yeah. Let's see. 15, sketch the velocity time graphs for the 3 bikers in figure 5.7. So figure 5.7, that goes way back to like section 5.1, I think. So it's on page 86. And we actually already calculated these velocities in the previous assignment that we graded, right? Remember, all we did with this is we just had to find rise over run. For A, we can just go over 1 increment and up 1 increment, right? So we rise by 2 and run by 0.2. Rise over run, 2 divided by 0.2, we said was 10, right? So the velocity of bike A is positive 10 meters per second. For part B, I think we have to get convenient places, we had to scoot over, we moved horizontally 3 increments and vertically 2 increments, right? So we rose by 4 meters and we ran by 0.6 seconds. So 4 divided by 0.6 was, 6.67, or 6.7, I think, to 2 places, 6.7 meters per second. And then wasn't bike C just like the reverse of that, right? We horizontally, we moved 3 increments and we moved vertically down 2 increments, right? So the rise was -4, the run was 0.6, so we just get -6.7 meters per second. So those are our velocities. Now if I'm gonna graph those in a velocity time graph, what's that gonna look like? What's that look like, you think? Olivia, so if I'm in a velocity time graph, now on that graph, what was it again, 5.7? Figure 5.7? What else can you tell me about those velocities? Are they constant or changing? They're constant because the slopes are constant, right? And that's the thing that we're really getting good at recognizing this. The slope of a position time graph corresponds to the value of a velocity time graph, right? Okay, so constant slope, constant velocity. So what would those velocity time graphs look like then? Just, yeah, horizontal lines, wouldn't they, right? They just would look like, the fast one would just be a horizontal line at positive 10, right? Because the velocity would be 10 and constant. The second fastest one would be a horizontal line at positive 6.7. And then the slow one would be where? Negative 6.7. Yeah, because it's going in the negative direction. Good, negative velocity. Very good. Okay, so 16. Yeah, this was kind of a lot of steps to this one. So a car is driven at constant velocity of 25 meters per second for 10 minutes. The car runs, when you think of this one, when you imagine it, do you imagine it kind of in the desert? I'm just curious, how many people did? Did you imagine it? Did you imagine this being kind of out in sort of like in the dry place somewhere in the barren? I sure did. I wonder, there must have been some common movies we've all watched or something, because that's sure the way I thought of it. Important that we got to the bottom of that. Yeah, there you go. So driven at constant velocity of 25 meters per second for 10 minutes. The car runs out of gas, so the driver walks in the same direction at 1.5 meters per second for 20 minutes to the nearest gas station. After spending 10 minutes filling a gasoline can, the driver walks back to the car at a slower speed of 1.2 meters per second. And so, yep. That's one sheet. That means it's important. So grab your stuff and head down and see what that's all about. Hopefully you can come back, but just take your stuff just in case. So, okay, and then Driver walks back to the car at a slower speed. I guess he's carrying that heavy gas can. Slower speed of 1.2 meters per second. The car is then driven home at 25 meters per second in the direction opposite to that of the original trip. So first of all, how many parts to that story are there? Count them up. How many did you get? See, I got 5. Is that what you got? Okay. So let's look at each of those 5 parts then. We're trying to draw a velocity time graph. So first part, the car is driven at constant velocity, 25 meters per second for 10 minutes. So on a velocity time graph, what's that going to look like? Straight line at pretty high velocity, right? High speed. It's going to be at 25 meters per second. So, okay, for a duration of 10 minutes, and probably be good to turn all this into seconds. So 10 minutes would be how many seconds? 600. Good. Okay. So that's part 1. Now part 2. The car runs out of gas, so the driver walks in the same direction at 1.5 meters per second for 20 minutes. What's that going to look like?
Wait,
Elijah.
what about when the car stops, like slows down?
Okay, so we'll being as that such a short time interval on this long graph, we'll just ignore that part. Yeah. So what do you think?
It looked the same, it'd just be lower.
Yeah, much lower. Good. Much lower. Instead of up at 25, it's down at positive 1.5 right? So very close to the t-axis, the horizontal axis. But it lasts a little longer, doesn't it? It goes for 20 minutes instead of 10 minutes. Okay, the third part of the story. What do you think, Brady? Third part of the story. After spending 10 minutes filling a gasoline can, so what's that 10-minute interval going to look like? Good. So it's a horizontal line at 0 because he's stationary, going nowhere, no velocity. Unless he's pacing, right? Exactly, which I would probably be doing. So after that, he then walks back to the car at a slower speed of 1.2 meters per second. Walks back at a slower speed. So Sydney, what's that going to look like?
Negative.
Ah, okay, good. So negative. Now we're below the horizontal axis because how come it's negative?
Because he's going back.
He's going backwards. So they told us that we're assuming they're starting off in the positive direction. So now we're going in the opposite direction, which must be negative. Okay. And then finally, last one, he drives home at 25 meters per second. So what's that going to look like? Alexis, what do you think?
Just like I had initially did, but negative.
Okay, good. Same as initially, but negative now. Okay, let me ask you this. Here's kind of a question that they didn't ask, but I'm curious what the answer is going to be to this. So if I were to add up the area under the curve, right, under the velocity time graph. Now think how we did this. We talked a little bit about this, right? We said that we assumed that any area that was above the horizontal axis, so above the t-axis, was positive area, right? And any area that was below the t-axis, the horizontal axis, was negative. If I add up the area of that whole trip under the curve, or it's not really a curve, but under the function, what do you think its sum is going to be? 0. How come?
Started at home and did that one.
Okay, because what is the area under a velocity time graph equivalent to?
Area.
What, I think I heard it. What was it? Displacement. Yeah. The area, we said a couple things, and that was the thing that we haven't talked as much about. We'll talk a lot more about that in calculus later. But we said a bunch of stuff about slope, right? We said that the slope of a position time graph is what? Slope of a position time graph, Ezra, what's that? Velocity. The slope of a velocity time graph is what, Deshaun? Acceleration, very good. And then we said the area under a velocity time graph is total displacement, right? So we know from the story that after that long, miserable trip this guy took, at the end of the day, he's at the same place he started, isn't he? So what's his total displacement? Yeah. Okay, make sense? We're going to get, the first part of the journey is going to give us the positive displacement. The second part, after he fills up his gas can, is all negative, okay? All right, so second part of that one was a little trickier, I thought. Draw a position time graph. using the areas under the curve of velocity time graph. Well, we're not gonna try to be too, but let's not worry about being too quantitative with this. Let's just be qualitative for now. So what's the first part gonna look like in a position time graph? What do you think, Nicole? When he's driving out into, he's leaving home in the morning, driving at 25 meters per second. Very steep and positive, good, right? Okay, second part, runs out of gas and is walking in the same direction. What's that gonna look like? Michelle?
It's still positive slope, but it's not as steep, not nearly as steep.
Good, not very steep, but still positive. When he's filling up the gas can, the slope is? 0, good. When he's walking back to the car, negative, but not very steep. And then driving home? Negative and steep, good. Good. Okay, that's it for that one, I think, wasn't it? So now 5.3, practice number 1. I like this one. I'm really, these are great because, to me, these are more important because we're starting to do some kinematic stuff. And so we're gonna start to get into the mode of using kinematics equations to answer important questions, right? Okay, so this first one. An Indy 500 race car's velocity increases from 4 meters per second to 36 meters per second over a 4-second time interval. What is its average acceleration? Okay, so this is one where we could even just use the definition of average acceleration. So without looking at your notes or anything, see if you can tell yourself here first. What is the definition of average acceleration? What do you think? Olivia, do you remember what the definition of average acceleration is? Good. Delta V, perfect, over delta T. Right, and it's really just T, isn't it? Delta T is really just T, exactly. So if we plug in this stuff, what is delta V? What's delta anything? If I say delta, whatever, delta Z. Finest minus initial, isn't it? It's always the final value minus the initial value. Perfect. So this is going to be, in this case, we're talking V's. So it's V final minus V initial, and delta T we said is just T, right? So we just have to plug that stuff in. So what's the final velocity? 36. Initial velocity divided by, and so we get what, 32 meters per second over 4.0 seconds is what? 8 or 8.0, I guess, but so 266. What are the units going to be? Good. Meters per, go away. Meters per, no, where is that? Meters per second squared, right? So 8.0 meters per second squared. Okay? All right. Moving on. $19, I think, was the next one. I love this problem. This is a good one. Forces you to think a little bit. A car is coasting backwards downhill at a speed of 3 meters per second when the driver gets the engine started. After 2.5 seconds, the car is moving uphill at 4.5 meters per second. Assuming that uphill is the positive direction, what is the car's average acceleration? Okay, so now you can always think about these as when we start and stop a stopwatch, or maybe even better, when we start and stop a video camera, right? So when are we starting the video camera, which starts with t equals 0? Say it again?
2.5 seconds.
That's the time, yeah. What's happening though when we start the video camera, what are we immediately filming? Okay, it's going backwards down the hill, right? When we stop it, after 2.5 seconds, it's moving up the hill, right? Okay, so then for this problem, what is our initial velocity? We'll be careful with this one. Everybody agrees -3? Why negative? Going down the hill. Good. So it's negative 3.0 meters per second. What's our final velocity? I don't have to put an F there. I could, but if we don't put an F there, remember, it just means final. We say V. So what's our final velocity? Positive 4.5. So therefore, what's delta V? Good, 4.5 minus negative 3.0, which is what? Positive and meters per second, good. And then our T? 2.5 seconds. And so therefore, average acceleration is just delta V over T, right? So average acceleration is just 7.5 meters per second, that's a 7, over 4.7. Ashamed of that 7, I got this there. 7.5 over 2.5 seconds. What is that? 3.0?
Yeah.
Units? Good. Make sense? Okay. Moving on. 20. A bus is moving at 25 meters per second when the driver steps on the brakes and brings the bus to a stop in 3.0 seconds. Okay, so now think about this in terms of the movie. Sometimes things aren't explicitly stated in these problems, but they're implied. So in that problem, what's the initial velocity? 25, because that's when I start the video camera, that's what's happening, right? Okay, so initial velocity positive. Okay, positive 25. We'll assume the bus is going in the positive direction. What's the final velocity?
0.
Ah, good. How come? Because it's coming to a rest. It stops. So the final velocity is 0, and what's the time?
3 seconds.
3 seconds. So then average acceleration is just what minus what? On the top. How am I going to get delta V?
0 minus 25.
Ah, okay. 0 minus 25 meters per second over 3.0 seconds. And so what's that going to give us? 25 over 3 is about, what, 8.3-ish? Okay. And it's negative, isn't it? 0 minus 25 gives us a negative 25 on top. So negative 8.3 to 2 places, meters per second squared. Now, why is it negative? Because I'm slowing down in the positive direction, right? So if this is the positive direction, here's me on the bus, slowing down, the invisible hand is pushing me backwards, in the negative direction, isn't it? Good, okay. Second part of this. Now we could, I like this, the second part is a good added twist to this. If the bus took twice as long to stop, how would the acceleration compare with what you found in part A? Now, we could just double the time and do the calculation again, couldn't we? But let's not. Let's think about this just in terms of the definition of average acceleration. If it's delta V over delta T, if I double the time interval, isn't that doubling delta T? So what happens to a fraction, to the size of the fraction, if I double the bottom? It's cutting it in half, isn't it? And really it's the same thing, isn't it? If I multiply the bottom by 2, isn't that really the same thing as saying 1/2 times the original? Right? Multiplying the bottom by 2 is like multiplying the fraction by 1/2. So I've really just multiplied the acceleration by 1/2. Okay? Makes sense, doesn't it? Okay? What would that feel like in terms of if you were on the bus? If the stop is very sudden, you feel the acceleration, you lurch forward. But if you extend, and we're going to talk about this more when we talk about impulse and momentum coming up. if we extend the time interval of the deceleration, then doesn't that smooth it out and make it feel less lurchy, so to speak, right? Okay. So you'd actually feel that difference. 21, look at the VT graph of the toy train in figure 514, okay? During which time interval or intervals is the speed constant? And it's a velocity time graph. So looking at that picture there, when is the speed constant, Nicole? What do you think?
5 to 15 seconds.
Does that make sense? 5 to 15? Okay, how come? Okay, because the velocity is, at that point, the function is constant, right? It has a horizontal, right? It looks horizontal, the graph does, which means that the value is not changing in time, right? Good. Okay, during which interval or intervals is the train's acceleration positive? Elijah, what do you think?
0 to 10.
0 to 10 is positive, isn't it? Okay. Where okay, during which parts of the journey, I'm going to ask you another question. Is the acceleration constant? Deshaun, what do you think? So we're still looking at that figure 5.14 on 97. So this wasn't one that was asked. Oh, no, it wasn't, okay. But I'm asking you anyway, just for fun. During which parts of the journey was the train's acceleration constant? Zero to 0 to 5-ish, okay, I'll buy that. Any other time? Yeah, how come? Elijah, how come? That's right.
15 to 20.
Yeah. How come those are places where the acceleration is constant?
Because it's wait. Oh, this is velocity.
Yeah.
Okay. Because the velocity is which means.
Okay, good, because it's linear, right? So the velocity time graph is a straight line there. Okay, that's true. There's actually one other one where the acceleration is constant too. From 5 to 15, sure. What is the acceleration from 5 to 15? 0, sure. Okay, very good. I guess there actually is one more part to that, isn't there? During which time interval is its acceleration most negative? Ezra, what do you think? During which time interval or intervals is the train's acceleration most negative?
From 15 to 20.
Yeah, that's where the slope seems to be the steepest. Good, in the negative direction. Okay, so same figure. We're looking at this graph. But what is the average acceleration from 0 to 5? What do you think from 0 to 5? Sydney, what do you get for the average acceleration?
2 meters per second.
Okay, what are the units going to be?
Oh, meters per second squared.
Yep, positive 2, right? Rise over run. It rises by the velocity changes by, right? So the graph rises by positive 10 meters per second when it runs by 5 seconds, right? 10 divided by 5 is 2, okay? Olivia, between 15 and 20, what'd you get for the average acceleration there?
Negative 1 meter per second.
Yeah, good. It rises, or excuse me, yeah, it rises by negative 6. So it's gonna be maybe not exactly, but close to it, right? It rises, so the rise is negative 6 meters per second, and the run is what? 5 seconds. So we're gonna get what, negative 6 divided by 5, so it's, what, about, close to -1, but about -1.2. And what would the units be? Good, good. And then finally, from 0 to 40, what's the average acceleration going to be, Nicole, from 0 to 40? 0, absolutely, because over that time interval, the velocity starts at 0 and it ends at 0. So the rise is 0 divided by, who cares what the run is? 0 divided by anything is 0, right? Good, very good. So why don't you just do this? Why don't you, on each of those assignments, just give yourself a grade out of 10 based on, if you did them all and you got them all or mostly all correct, give yourself a 10. If you did half of it or got them about half correct, give yourself a 5. If you didn't do it, obviously have to be 0, or someplace in between. So it's just kind of a judgment call. It's not worth very much anyway, but just, to make it worth something. Circle it. I'll get it tomorrow. That is, you just can't teach that. That kind of timing. Where you end right on the bell, So back in the lab tomorrow.